Well, good afternoon, everybody. I'm extremely happy to be able to talk to you this afternoon. Even it would be nice to have these sort of events face to face, but unfortunately, it cannot be realized at this time. So it's good to see you all and talk to you even virtually. What I'm going to, I told Henry that I will have this presentation available for everybody. So because I most likely not going to be able to go through the entire presentation. And since my goal is to tell you what we do at the center, but also invite you to participate if you recognize any overlaps with what your work is, or if you like to know more. So it will be available. I'll send it to Henry and he can post it and you guys can download it. I would like to give you a very, very quick overview of the Center. The Center for Environmental Systems, its mission and objectives are aligned with the Stevens Strategic Research Plan, obviously. And we have realigned in the area of, let's call it energy and environmental sustainability, but without abandoning our core competencies in the area of environmental technology for remediation or wastewater treatment. So the center was established in 1988. It has a laboratory floor space of about 10,000 square feet and equipment infrastructure of costing over $11 million. We do have an annual budget of about research expenditures of about $3 million a year. We also organize an international conference every 2 years, and we like to be part of the commercialization process at the university, and we've done that successfully in the past. In terms of publications, the center puts out about 25 peer-review articles per year, and our Scopus index for the center, that is work that is done and published by the center affiliate faculty, is about 52. So we're trying to keep track of our scholarly output as well. This is a list of people that are currently in different ways collaborating through the center among themselves and with other universities. And if you take a quick look, you will see that there are people from all walks of life and also from different departments and schools. And that's why I like to look at the center as a resource for the entire Stevens community. In the past, I have personally collaborated with people from the School of, now we call it School of Business, but it was School of Technology Management, and we managed to get actually very basic grants to investigate technology transfer, environmental technology transfer through NSF. So you can do, there are opportunities to conduct research in different areas through the center. And what I like to do, now I know I'm going very quickly through this, but like I said, they will be available, the presentation to you. So if you look at our major technology initiatives, and there is no particular order, but we do work in the renewable and sustainable energy sector, water and wastewater treatment, and nutrient recovery and reuse. This is all really falling under the sustainability umbrella, if you wish. 2 and 3 actually can very nicely support number 1, which is renewable sustainable energy. And I'll go through an example to show you how we can achieve that. Let me just give you an overview of a big project that we've been working on for a number of years, and that is using, look at the munitions facility. Munition facilities are run by the Department of Defense, and that's where all the explosives and energetics are produced. And the idea is to look at these facilities and the waste streams that they generate as resources in order to achieve what is called in the Department of Defense and in general in our field, a net zero outcome. Net zero in terms of waste, energy, and water. So in other words, you want to minimize the environmental footprint in terms of your CO2 loads and also waste and water. So if you look at the facility like this, there is a lot of waste streams that contain valuable compounds, such as nitrogen in the form of nutrients. The idea is, can you recover these nutrients and use them to produce biomass? So we do a systems approach at the beginning to identify the different budgets, or balances, if you wish, in terms of mass balance, water balance, and energy balance. And then you can propose different scenarios with the idea that you develop technology that will help you reach your target, which will be this net zero concept I just mentioned. So if you look at the different waste streams, they can be liquid streams, mostly wastewater, very rich, as I said, in nitrogen. Can I directly take them as is and produce biomass, let's say, in the form of algae? If the answer is yes, then you can go ahead and try to produce the algae in those streams, and of course assess your productivity and then what you do with it, with the algae biomass. If not, can we have some pre-treatment? And you see now how this, the general technology initiatives fit into each other. And we treat it in order to make them amenable for biological growth. So for instance, let's say that we have a stream that works very nicely. We grow our algae biomass. We take that biomass and we see it now as a resource, which can be, in the case of algae, production of oil, algal oil, which you can upgrade to biodiesel, for instance. Economics are very difficult there. Or you can produce biogas through anaerobic digestion. For instance, you can apply two-stage anaerobic digestion to produce hydrogen or methane. So this is really, we look at a large system and we see how we can manage, because managed practices are also extremely important, manage the entire operation with the goal of achieving a sustainable system. So like I said, to grow biomass, you need carbon, nitrogen, micronutrients, and energy, which in the case of plants like algae, it comes from sunlight. And their waste streams provide you this carbon and nitrogen, and carbon can be in the form of CO2 because that's what plants take, then you are in good shape. As I mentioned, we do go through a toxicological testing to assess if these streams can support algal growth. If water stream is toxic, we can treat it to mineralize. And what it means in environmental parlance, to mineralize organic compounds, it basically means to convert them to carbon dioxide and very simple nitrogen forms such as ammonia, nitrate, nitrite, and remove heavy metals if present. There is a word missing there at the bottom of the slide. Heavy should be metals after that. So if that's if in the case where you don't need to treat the streams, you can take it as is, or if you need to treat it, you treat it and then you start growing your algae. And as you can see, we start with small on the right left up corner of the slide. We start with flask and microcosm bottles to determine the growth rates, and then we scale up, and you can see in the bottom left the 100 liters raceways reactors that we use for algal growth. And on the right, you can see the setup in the lab. So the idea is that we take this process, the entire development, all developmental phases till we're ready to do a field pilot. The amount of biomass that you generate in liquid form has kind of a theoretical minimum, a maximum rather, of about 1 gram per liter, which is really not very concentrated. And that's a big issue, how you concentrate algal biomass. There is a desperate need for technology development in that space. So we managed to actually produce 8 grams per square meter per day, which is very comparable to what you see in the industry. And remember that these are using streams that were wastewater streams. So there is the proof of concept that you can use the wastewater from these facilities to produce a valuable resource, which is biomass. Another way to produce biomass, algal biomass, like all other microbial biomass, is an attached form. And you can see we're running experiments in that space, in that area as well. The advantage is that you get a much more concentrated biomass, and you can attach them in different media. That can be a solid media, it can be cloth, and people have been using different sort of substrates. The idea here is that you can scrape the biomass by some mechanism and get a much more concentrated. From 1%, you can go probably up to 5 or 6%. So you are reducing the energy requirements for concentration of the biomass, which is really can be a showstopper. And this is what the biomass looks like after you concentrate it to about 10%. So this is what you can do in these facilities, but in order to reach this stage, as I said, you need to support your operations with technology that allow you to pre-treat these streams and recover nutrients. So then, as you can see on this slide, you can start the extraction process. What you see here is a small oil extraction chamber, and this shows pretty much the flow from harvesting, concentrating, and then extracting the oil in a small scale. And here is a large 70 grams pilot extractor that we have designed and we have in our lab. The other, if you recall, the other way to work with this biomass is to anaerobically digest it for methane production. We have scaled that up. Actually, we have a unit in the basement of McLean, which produces biogas, methane in our case. And then Professor Besser actually is working to take that stream directly into a fuel cell. So you see that you can branch down into all kinds of different areas through this project. Now, there are certain streams that they just waste streams that contain very high concentrations of chemicals. In a case where during the production of RDX, there is a waste stream generated with ammonium nitrate. And ammonium nitrate is what we call a monofuel, which can be directly utilized in a combustion process. And Nick Proizal is working on this. I don't know how much Nick will tell you later, because some of this is also ITAR control. But you can see how broad you can go as you work in these facilities. Actually, we're at the point in this technology, we're building now a continuous flow energy reactor. So let me very quickly go, and I think I have another minute, take you through some of the technology that we use to mineralize the organic chemicals, which are mostly cyclic compounds, nitro, like RDX or Cl20 or other explosives, even nitrocellulose. We use different processes, both oxidative and reductive processes. And here I'm showing you a catalyzed reductive degradation using bimetals and also a UV-based phenton-like oxidation process. And the goal here is to reduce these organics to CO2 and nitrogen, so you can utilize these smaller molecules for production of biomass. This is another technology where we have the UV basically in a smaller scale. And this is UV combined with hydrogen peroxide. And this is a scale-up unit that we built at Picatinny Arsenal to carry out this process. Again, you can see how the development goes from bench scale, from proof of concept all the way to pilot scale. Of course, after that, it's up to the customer to take it and apply it. This is another technology where we have developed composite iron particles for treatment of explosive compounds and also arsenic and chromium. So heavy metals can be also treated. As I said, this could impart toxicity, so you need to remove them if you are to use the wastewater stream for biomass production. And I'm almost done. I have 2 more slides. Let me just show you 2 technologies that we've developed for nutrient recovery and reuse. And by nutrient recovery here, I mean nitrogen in the form of nitrate and nitrite or phosphate. And this is a technology where we use green chemistry to develop and test fractionalized cellulose nanoparticle as an anionic resin exchanger for the removal of phosphates and nitrates from aqueous solution. This is actually, I just graduated a PhD student on this, and that was really a nice project. And she published a few papers out of this work. And this is another technology that Valentina Pricobe is working on. How do you take carbon dioxide from the atmosphere or any source, basically, put it into a mineral form, and then you can take the mineral as a CO2 carbon source for algal growth. This is a pretty neat project that could also lead to some very basic research. This is, I mean, again, here we look at CO2 as a nutrient, which is actually a carbon source, but you can call it a nutrient for our purposes here. And that's what I have. There is a presentation that shows you a larger scale of production, which you will see in the slides, which I will forward to Henry, and he can make them available to you. So we're running a large pilot scale, 2 1,000-gallon reactors at Holston, and we did it last summer, and we have the optimization study this summer. And with that, any questions? Thank you.